Hi everyone, I'm Eugene from Monash University. Today I'm going to present our work, Robustness of On-Device Model Adversary Attack to Deep Learning Model on Android App, which is authored by Yujing Huang, Han Hu, and Chunyang Chen. Currently, mobile apps play a vital role in our daily life. People can use them for shopping, banking, and even monitoring healthy conditions. With the popularity of deep learning and its excellent performance in many domains, many mobile apps start to adopt deep learning model for supporting advanced functionality such as image classification, face recognition, and object detection. Deep learning-based mobile apps often integrate on-device model to perform core functionality. The model inference is faster as it is executed on smartphone. However, the on-device deep learning model provides hacker a chance to attack them. Specifically, most model files can be easily obtained by decoupling Android app without any protection mechanism. Model exposure may cause intellectual property infringement or allows hackers to access model files to produce malicious attacks like adversary attacks. Since training a deep learning model from scratch is time-consuming and high cost, stealing models from or use them without permission is illegal and harmful to the original companies or developers. Moreover, many mobile apps are used for important tasks such as finance, social, or even life-critical tasks. Attacking the model inside those apps will be a disaster for end user. Thus, motivated by this, we carry out an empirical study to investigate the characteristics of deep learning model in real-world mobile apps and design a simple but effective way to adapt existing adversary attack to investigate the security of this app. We present our result by answering three research questions. The first one, how similar are TF-like models used in mobile app? And how widely pre-trained TF-like models are adapted? And how robust are fine-tuned TF-like models against adversary attack? The reason for choosing TF-like model is that TensorFlow Lite is the most popular framework for implementing deep learning in mobile devices in recent years. To enable our research goal, we design and implement an analytical attack pipeline including model digger, model comparer, and model attacker. The first step is identify TF-like deep learning app and extract models from them via the model digger. It decompiles Android APK, then search TF-like model based on the specific naming convention. After obtaining the model comparer is used to discover the relation between the extracted TF-like model and locate the fine-tuned model among them. The core idea of the model comparer is detecting the longest common sublayer between two TF-like models, then calculating the similarity between them. Finally, the pipeline evaluates the adversary robustness of the identified fine-tuned TF-like model while model attacker, which is able to perform 11 adversary attack algorithms. To present the result of RQ1, we use community detection to group highly related nodes in the graph, as shown on the left side. Each node represents a TF-like model, and an engine between two models indicates there is a relation between them. The thicker the engine is, the stronger relation between two models. Among 267 extract TF-like models, about 87% of them are structurally highly similar, and about 79% of them have the same parameter to at least one model. Surprisingly, 182 models are exactly the same in terms of structure and parameter. Moreover, 15 models across different task domains such as object detection, image classification, and image segmentation have relations with other models. The relation for models within the same task domain are typically stronger than those from different task domains. Based on the analysis for RQ1, many deep learning models across different mobile apps are very similar. Thus, we further explore whether the model similarity is caused by fine-tuning the common pre-trained model, as fine-tuning techniques are widely used in deep learning area to reduce training overhead. Our results show that 14 extracted TF-like models are fine-tuned based on the pre-trained model from TensorFlow Hub. which is a repository contain pre-trained TF-line model for fine-tuning. Among these fine-tuned models, nearly half of them perform computer vision-related tasks like image classification. As mentioned in RQ2, most fine-tuned models perform computer vision-related tasks, and their pre-trained models are publicly available. Hence, we select 10 representative fine-tuned TF-line models for evaluating the adversary robustness. Our results show that all selected models are successfully attacked, with an average of 23% of adversary samples are wrongly classified. Moreover, our results demonstrate that the target attacks are more than 3 times better than blind attack in terms of the attack success rate, which indicates that locating fine-tuned models pre-trained model can highly improve the adversary attack success rate. According to our study, model plagiarism is a real-world problem in deep learning-based mobile app, which may caused by developer reusing the deep learning model file of other or retraining a new deep learning model on top of it. Thus, it is essential to take necessary measures such as watermarking and file encryption to protect the intellectual property of the on-device model. On the other hand, perform deep learning on device provide hacker a chance to apply white box adversary attack to this model, as they can easily obtain the model while reverse engineering, which makes deep learning-based mobile app more vulnerable and may cause a negative impact on end user. Therefore, we encourage developers to take measures for preventing disclosure of model information like model parameter. To wrap up, model plagiarism problem is existing in deep learning-based mobile app, and on-device deep learning models are vulnerable to adversary attack. In future, we will work on both the attack and defense side of on-device model. Thanks for watching.
Hello, everyone. I hope that you all enjoyed Eugene's presentation. My name is Grace Lewis, and I will be chairing this session. If there are any questions for Eugene, please type them in the chat. In the meantime, while you get your questions ready, I would like to ask Eugene a question. Thank you very much for the talk, Eugene. A very nice exploratory study. So when as I was watching your presentation, I saw that you presented an interesting trade-off, or another word is to say dichotomy. So because on the one hand, being able to reuse models saves a lot of time, of development time. But on the other hand, if you reuse models, then you are more vulnerable to adversarial attacks, and therefore, for example, developers could decide to start from scratch, right? So you can either do it fast and reuse models, or you can take your time and do it slow and reuse models. So how do you solve that problem? What is your advice? I mean, is it better to reuse? Is it better to start from scratch? What is the middle ground?
Yeah. Actually, for this point, I suggest the reuse the model will be the best choice for the industry, especially because in industry we don't have too much time to train the model from scratch, no matter in the data aspect or in the cost aspect. Because in the industry, we always have the limitation on the resources that we can apply. So as a developer, I suggest the developer, especially the AI and the mobile developer, they can just use the pre-trained model and then leverage the pre-trained model's ability to adapt them to their own individual tasks. But when they use this model, they need to consider the security. So, for example, if you just take the model and then slightly modify it and then put in your device, that will be very vulnerable to the to your application, because the developer can just take your model out and then just analysis. It's easy to find the pre-trained model. So the best choice you can do is like you need to do some encryption for your model, or do some like adversary training or something like that to make your model more secure or unclearly to the attacker. It's like the attacker cannot directly find what kind of model you use. Yeah.
Okay, thank you. That was good. Are there any questions for Eugene? Okay, so I can ask another question. So Eugene, while we were in the backstage, you were telling me that this is the result of your master's work. So congratulations.
Yeah, thank you very much. Yeah.
What are next steps for you? Where do you want to take this work as you go into your PhD?
Yeah, actually, currently we are just continue to this area. It's like in this paper we only discover the vulnerability of the on-device model, but we can't provide a specific way to attack the on-device model. So in the next step, we are going to develop a model-specific attack. So for example, like MobileNet V2, Inception, etc. We're gonna develop a specific method for different kind of model, and then to enhance our attack ability.
Okay, thank you very much. We do have a question from the audience now, from Jen Sehuan. It says, "Hi Eugene, how do you generate adversarial examples? I mean the attack methods that you choose."
Yeah, so for generate the adversary example, so we adapt the existing adversary attack algorithm, because in this paper we only want to test the robust of the on-device model against the adversary attack. So we don't develop any new adversary attack. We just adapting the existing one to test the robustness. Yeah.
Okay. Are these, do you think these methods are enough? Because there's a lot of work in this area, right? Trying to generate, test cases for not necessarily on device models, but DNNs, for example, in general, deep learning. So are these, do you think these testing methods are enough? Going back to the idea of industry?
I think this is not enough, because the setting of the on-device model is different from maybe the cloud side or the traditional machine learning model, because in the on-device model, the hacker have more ability to investigate or to to find out what kind of the model, the characteristic of the model, so they can generate or develop a more powerful adversary attack against this type of model. Yeah. Okay. It's the setting is different. Yeah.
Right. So a question from Thomas Welsh. He says, "Sorry, I missed some of the talk, so I might have missed it, but is your tool set available somewhere like GitHub?"
Yeah. The code is publicly available. Yeah, it's in the GitHub. I saw that. I think the link is in my paper. Yeah, you can find it in the paper. Yeah, inside the paper. Okay,
great. This will be good. Are there any other questions? Okay, so okay. Oh, actually, there's another one here. Great. From Inés Valentín, are you considering taking those fine-tuned models, applying a defense mechanism to them, and then assess the effect of the efficacy of the attacks on those defended models? The question is in the chat if you would like to look at it.
Where I can look at the.
Are you considering taking those fine-tuned models, applying a defense mechanism to them, and then assessing the effect on the efficacy of the attacks on those defended models?
Oh, yeah. Yeah, it depends how you want to adapt the model. But I saw if you are considering use that kind of model in the maybe security critical application, then you may too careful think about it. Yeah.
Okay. So a question about on-device models specifically. So obviously, devices are resource constrained, as you well know. And so a lot of times what happens before you deploy a model on these devices is you do some type of compression, some type of pruning, right? To be able to make the model smaller so it runs on devices. In your study or what you've been doing, does that process make them more vulnerable?
Yeah, actually, when you convert the traditional model to the on-device model, you will convert the model from the some kind of the PB file to the flattened file. Yeah, and then that kind of file we use some quantization technique. Yeah, that will introduce more vulnerable, because the quantization technique in the popular machine learning framework is publicly available. Attacker can just explore that kind of the quantization technique to know, what kind of technique you use, and then we just developer adversarial attack or other malicious attack against that kind of the quantization technique. Yeah.
Okay. We have another question from Jen Huang. Says, do you test the transferability between these Android apps using the same adversarial examples? If so, can the same adversarial examples attack all your chosen 10 real-world apps?
Does that mean I only use the adversarial example generated from one on-device model only, or other kind of model? I'm not sure about how what the transfer mean in the question.
Jinsei, can you clarify what you mean by transferability? I think, yeah, he said the answer is yes.
Oh, yeah. No, you can't, because different model apply different transfer learning approach. Then it depends on the how many layer you fine tune in the pre-trained model. Then the adversary attack success rate will change case by case. Yeah, you can't just apply only one model and then transfer to another one. This does not make sense. Yeah.
Okay.
Yeah.
Okay, so transferability, this is a clarification from Jen said, transferability means one adversarial example can also attack other apps. So yes, I think you answered, I believe that's what you answered.
Yeah, you can't. You must be case by case, do it case by case. Yeah.
Okay, so another question from Thomas Welsh. Considering you mentioned proprietary models, do you find barriers to research associated to intellectual property of some models? Following from the previous question too, about future defensive approach research.
I don't think about this. Yeah. I'm not sure about how to do that kind of work. Yeah, I have no idea. Yeah. Sorry
so
about
given
that
we no problem. Given that we have 5 seconds, this is perfect. We'll see you. Thank you.